Hey everyone, and welcome. Today, we're going to crack open the devices we all use every single day, not to see how they work, but to find out what happens when they just stop. We're about to dive into the incredible science of turning our electronic waste into a seriously valuable resource. So, think about that old phone you have stashed away in a drawer somewhere. What if I told you it's not just junk? What if it's literally a tiny gold mine? Well, it is. Yep. Locked inside all that plastic and glass is a treasure trove of precious metals. And in this explainer, we're going to see exactly how chemistry gives us the key to unlock it. Okay, so first things first, we really need to get a handle on the sheer scale of the challenge we're up against. We all love our gadgets, right? But they create this massive and constantly growing mountain of digital trash. And this brings us to what's called the e-waste paradox. On one hand, yeah, this waste is a toxic hazard, leaking all sorts of dangerous stuff into our environment. But on the other hand, it's a hidden treasure. And get this, the concentration of gold in some e-waste can be way higher than what you'd find in ore pulled from an actual mine. In an age where resources are getting scarce, this isn't just trash, it's a strategic reserve. So the big question is, how do we deal with the hazard and unlock the treasure? Well, the answer lies in this really fascinating field of chemistry. So let's meet the hero of our story, hydrometallurgy. To put it simply, hydrometallurgy is kind of like metal processing with water, or to be more precise, with water-based chemical solutions. Instead of using insane amounts of heat to smelt and burn everything apart, this method uses these carefully designed liquids to just dissolve and pull out the specific metals we want. The whole process breaks down into three pretty elegant steps. First, you take the crushed electronics and toss them into a chemical bath. This dissolves the metals, creating a kind of metal soup. Then chemists use special agents to separate out the specific metals they're after. It's like having a chemical key that only unlocks gold. And finally, the pure metal is recovered from that solution, ready to be used all over again. All right, so let's go a little deeper now. Let's peek into the chemist's lab and look at the actual recipes they're using to go after these different metals. This really shows you how precise this all is. The active ingredients are called leaching agents, or lixiviants. For gold, the traditional go-to has been cyanide, but now researchers are testing newer, greener organic agents. For metals like copper or the rare earths, powerful inorganic acids are the tool of choice. You can think of it like having a selective fishing net for each type of metal swimming around in that chemical soup. So what are we actually fishing for? Well, the haul is just incredible. We're not just talking about gold and copper. We're recovering palladium, which is essential for electronics, cobalt for our batteries, and even those super important rare earth elements like neodymium, which are vital for magnets in everything from your headphones to electric cars. This, right here, is the circular economy in action. And the efficiency? It can be absolutely staggering. Some research shows that under just the right conditions, the right temperature, the right timing, the perfect recipe, you can achieve recovery rates for some metals as high as 98.7%. So yeah, this isn't just some theory. This is a highly effective process that really works. But you knew there was a but coming, right? As with any powerful technology, this is not a perfect solution. We have to be honest about the trade-offs and the environmental costs that come with it. And here's the central conflict. On one side, you have the promise, a super efficient way to reclaim critical resources and clean up a toxic mess. But on the other side, you've got the problem. These chemical processes can demand a whole lot of energy, and they create their own secondary wastes that have to be managed, which, of course, adds to the cost. This quote from the research really just hits the nail on the head. The science works, for sure, but making it economically and environmentally sustainable on a massive scale, well, that's the next great challenge for engineers and chemists. And that brings us to what I think is the most exciting part, the ongoing search for even better, greener, and more efficient methods. Because the innovation here has definitely not stopped. This gives us a little peek at where the science is going. Scientists are developing greener chemical recipes that have fewer nasty side effects. They're exploring ways to use seawater as part of the process to cut down on the need for fresh water and certain chemicals. They're also fine-tuning solvents to be even more selective, and even looking at brand new methods, like something called molten carbonate electrolysis, that might avoid using harsh acids altogether. So, as we look to the future, The question really isn't if we can mine our digital mountains. We know we can. The real question is this: how quickly can we perfect the science to turn what has been one of our greatest waste problems into one of our most valuable and sustainable resources? The answer to that is being written in labs right now. Thanks so much for watching.